The first core principle of calculus is something called the limit. In a broad sense, all a limit does is show what number the output of a function approaches as the input value gets closer to a particular number. Before we dive too deep, we'll learn how to read and write the notation of a limit. We have the word lim, simply identifying this as a limit. Then there's this x with an arrow pointing to an a. This just means the x value that we are plugging into the function is approaching some number that is represented here by an a. Then we have f of x. This is our function for which the limit is applied to. Finally, we have this entire thing equal to some L, which represents the output of the limit. Altogether, this reads as the limit of f of x as x approaches a is equal to L. This may seem confusing and a lot to digest at first, but the concept is actually quite simple. Let's see a limit in action. So here we have the function f of x is equal to x squared. Let's say we want to find the limit as x approaches 0. There are two ways we can solve this. The first we'll see by looking at its graph. The way we find the limit is by following the line on both sides until we reach the specified x value. Here we are given that x is approaching 0. So if we trace the line to where x equals 0, we see that the y value is close to 0. The second way we can solve this is by creating a table of inputs and outputs. And just like when looking at the graph, when we calculate the limit using these tables, we have to find values using inputs that are less than and greater than the x the limit is approaching. One of the best ways to find inputs that continuously get closer to the number x is approaching is by adding and subtracting 1 from it. We then can add or subtract a number that gets us close to our limit, but never exactly to it. In this case, we're approaching 0, so we start with the inputs -1 and 1, then work from there. We can then start by adding 0.9 to -1 and subtracting 0.9 from 1. We continue this pattern with 0.09 and 0.009 until we get numbers very close to 0 but never exactly 0. As the table shows, the output gets extremely close to 0. We can now definitively say that the limit of x squared as x approaches 0 is 0. Let's look at a few other trivial examples. Here we have sine of x divided by x. And let's once again find the limit as x approaches 0. You may have noticed in the last example that you can plug in the number that x is approaching and receive basically the same number. This method only works when the function is continuous over the interval in which the x is approaching. In this case, there's an infinitely small hole in the function where x is equal to 0. So when we plug in 0 for x, we get a fraction where the denominator is 0. This fraction is in an indeterminate form. We cannot derive any conclusions from a fraction in indeterminate form. A function like this is why limits are so important. By looking at what happens around the function when x equals 0, we can see what the value of the function appears to approach. Again, we have two options, looking at the graph or a table of values. Let's first look at the graph. Using the same method as before, we trace the graph to x equals 0 and see that both arrows lead to y equals 1. Now, we can switch to the table. And again, like before, we'll start with an input of 1 and reduce by a factor of 10 for both positive and negative values. Here we can see we get the same result that we got from the graph. Therefore, the limit of sine of x over x as x approaches 0 is 1. Another example that shows how a limit works is this piecewise function. As you can see, the graph of the natural log of x is continuous everywhere except for where x equals 2. According to the piecewise function, it returns a value of 4 when x equals 2. So what happens when we want to find the limit as x approaches 2? Could it be 4? If we recall, a limit is only concerned about what the function does around the x value we're approaching. In this case, we can simply ignore the dot up here and see what the main graph does. By following the arrows, we can see that the graph approaches a value of approximately 0.69315. And here's a table that gives us the exact same conclusion. There is one more case to explore with the limit. Not every limit can be found. Let's look at a quick example. Again, we will look at a piecewise function. This one in particular is called a step function because, well, it looks like a step up or sometimes a step down. Now let's find the limit as x approaches 0. As you can see, the arrows never reach the same spot, and they never will no matter how close we get to 0. Well, maybe we just can't see it with our eyes. Maybe the table will tell a different story when the numbers get super small. Nope, same answer. In cases such as these, the limit does not exist, or D&E for short. Let's look at another example where the limit does not exist. Here we have the function sine of pi over x. It appears to be like any other regular function, but looks can be deceiving. Let's find the limit as x approaches 0. Looking at the graph, as x starts from negative infinity and makes its way towards 0, it appears to be any average function, but yeah, this happens. This portion right here is caused by a rapid increase in oscillations over a very short period. The tracing method fails us here because we can't see exactly where the function settles at 0. So we must look at the table. As the x gets smaller and smaller, we can see the y value just bounces between positive and negative numbers. Since the y never reaches a single value, we once again say the limit does not exist. That concludes this video on limits. I would like to thank you all for watching, and especially making it this far in the video. Your calculus journey has just begun, so don't forget to click that subscribe button and turn on notifications so you won't miss the next video. Bye for now, and I'll see you in our next lesson.